Here's a problem on conservation of energy. The main idea we want to keep in mind whenever we're solving an energy problem is that energy is conserved. Energy is never created or destroyed, just transferred. As far as we know, the energy in the universe is absolute. It means there's an amount, and it's just transferred, transformed into different types of energy. So that means if we looked at one system, meaning we just draw a box around something, like your teacher standing on the ground holding a pen up in the air, that the energy in that system remains constant unless something outside that system does work on it, or unless the system itself does work on something outside. So picking up a pencil off the table, for example, you are doing work on the table because you're applying a force over a distance, giving it energy, and lifting it up in the air, which gives it gravitational potential energy. So in all of these formulas, our total energy, E sub t, will remain the same. And right now we're just going to look at gravitational potential, which means energy due to distance from the ground, kinetic energy, the energy of motion, and dissipated energy, energy that's lost as friction or heat, that sort of thing. So the first type of energy is gravitational potential energy. So that's equal to the mass of an object times acceleration due to gravity. Remember, that's 9.8 meters per second squared on Earth. And you multiply that by the height it is off the ground. So this is just saying the higher an object is from the ground, the more gravitational potential energy it has. Well, that seems to make sense because the higher it is off the ground, the more distance it can fall, and we know as it falls it increases its speed due to gravity. So greater distance from the Earth means more gravitational potential energy. And as you let go of something and it falls towards the Earth, as its velocity increases going down, then its kinetic energy goes up and the potential gravitational goes down. But that means the total energy in the system remains the same. Let's look at what kinetic energy is. Kinetic energy is the energy of motion. That's 1/2 times the mass of an object times its velocity squared. So we abbreviate that E sub k to be kinetic energy. So where m is mass and v is velocity. Mass in kilograms and velocity in meters per second. Greater mass means more kinetic energy. Greater velocity means much more kinetic energy, since velocity is squared to give us the kinetic energy. This is also just a heads up that this is where you want to look at square roots and what it means in terms of a relationship. Kinetic energy increases much more quickly as velocity goes up, as opposed to when mass goes up, because of that power of 2. Dissipated energy is energy lost from the system. So one example would be if somebody's skateboarding down the hill and they power slide, which means they turn it to the side really quickly and slow down very quickly. What happens if you were to pick up your skateboard right afterwards and feel the wheels is they're very hot, because the friction from turning the wheel sideways going on the ground heats up the wheel, and that heat is dissipated energy. So we're going to refer to it as something where just energy is lost from the system. So we know if we're holding an object up high, once all the energy it has is due to gravitational potential energy, as we let it go, the height will get lower, so this amount of energy will go down, but the total energy will remain the same. It's just getting converted into kinetic energy. So let's look at a problem involving this. 8th grade egg drop competition. One student wants to know how fast the 0.1 kilogram egg will be going as it heads towards the ground after dropping it from 40 meters. She wants to know halfway to the ground and right before making impact, how fast will it be going. So assume she drops it from rest here, meaning the velocity is 0 when she drops it. Remember how we set up problems? First we draw a picture. So here's the building. There's the egg with no velocity at a height of 40 meters. There it is halfway down at 20 meters, and there it is right before impact. Assume that this distance is essentially 0, just immediately right before it hits the ground. Remember, we identify what we're looking for: total energy, gravitational potential energy, and kinetic energy. To simplify this problem, we're going to assume that no energy is dissipated, meaning no energy is lost. So all this gravitational potential energy converts to kinetic energy as you go down. So before we start these problems, it's important to get that concept. Here there's no velocity, so there's no kinetic energy. All the energy of the system is gravitational potential energy. As it drops, it gets closer to the ground. So that total energy is kinetic and potential. So it gets lower. As its velocity increases, it gains kinetic energy. So the kinetic energy loses gravitational potential, and that's converting it, transforming it into kinetic energy. At a height of 0, it's going to be essentially 0 meters off the ground, and all that energy should be converted into kinetic energy. So our first step is going to be how much energy does it start with total? We know that total energy is going to be the total energy it has at each of the other points in the fall. And then we're going to identify the information we're given. Starting height is 40 meters. The mass is 0.1 kilograms. No energy was dissipated. And the acceleration due to gravity, g, is 9.8 meters per second squared. We also have this key concept that energy is conserved, meaning the total energy remains the same throughout the drop. So all that gravitational potential energy is slowly converting to kinetic energy. Relationships and formulas are what we identify next. So here's the idea of energy conservation. Energy is not created or destroyed. Here's the formula that refers to that. So our total energy, that will E sub t will remain the same throughout the problem. Here's our gravitational potential energy formula, and here's kinetic energy. So I'll go ahead and solve the first part of this problem for you, and then I'd like you to solve it at 20 meters and 0 meters. At 40 meters, all the energy is potential energy. It has 0 velocity, so we know it's only potential energy due to gravity. So when solving these problems, think about what's the easiest thing to solve for first. Here, the easiest thing to solve for is the kinetic energy at the top. Let's look at the picture. At the top, it's all kinetic energy. There is no gravitational potential energy. So we know all the energy right now in this system is due to its distance from the ground. So we just have to worry about the one formula to find the total energy. So that formula is mgh. So the mass is 0.1 kilograms. The acceleration due to gravity is 9.8 meters per second squared. The height off the ground is 40 meters. That gives us a total energy of 39.2 joules. Now when doing these problems, remember that this number is very important. That'll be the total for at 20 meters and 0 meters. All the energy that's in the system is right there, as long as no work is done on the system and as long as the system doesn't do work on anything else. So at 20 meters, we're going to have a total energy of 39.2, which is written here for you. And then at 0 meters, we're going to have that same energy of 39.2 joules. So we need that value in order to solve the next step. Now at the second step, we know that it has fallen halfway. So the height is halfway to the ground, so half of 40 is 20 meters. Now we know it has a velocity, so it has both kinetic energy and gravitational potential. However, we know when we add those up, they equal 39.2. First, I'd like you to solve for the gravitational potential here. Plug that in. You know the rest of the energy must have turned into kinetic energy. So then solve this formula down here for kinetic energy. So figure out how much is gravitational potential. We know we'll have to subtract that from 39.2 and then solve for the velocity there. So we know what's left must have turned into kinetic energy as it's falling. And then solve for the velocity using that. Here's a little note to help you remember that the square root is like undoing when you square a variable. Just like division is the opposite of multiplication, a square root is the opposite of squaring a value. So here we had all gravitational potential. Here it's been turning into kinetic energy. We still have some gravitational potential because it's halfway to the ground. Here at the bottom we know the height is essentially 0 meters right before it hits the ground. So here we'll have all kinetic energy. So use that to solve at 0 meters. And then just remember that our last step is to check to make sure your answer is reasonable. So take a look at it. If you got kinetic energy here that was bigger than 39.2, for example, you know you did something wrong. No work is done on the system. No work goes out of the system for our purposes. So we're saying that your value here must be less than 39.2. Here we know all the potential energy must be 39.2. All the kinetic energy must be 39.2 joules because it's has no height off the ground. And then just finally keep in mind that energy is conserved, meaning not created or destroyed, and that's the key to all these problems. So you want to find the total energy at one point and know that that's going to remain the same at all the rest of the points.